Today I'll be talking about finite fields and their applications. So let me start with describing finite field representation. So a finite field is represented by finite field with argument p, which is a prime, f, which is a polynomial function irreducible over zp, and rep, which indicates the representation used for finite field elements. It's either polynomial or exponential. So P is called the characteristic of the field, F is called the field irreducible of the field, and the degree D of F is called the extension degree of F over Zp. And the field of F has P to the power D elements, and the elements are indexed by integers between 0 and P to the power D minus 1. So for instance, this will construct the finite field with 17 to the power 3 elements. So now let me discuss shortly the two representations that we have. So in the polynomial representation, the field element is represented as a polynomial in the field generator, and the index is computed by using the polynomial coefficients as digits with base p. So for instance, if we extract this element with this coefficient list, then index will be the coefficient list dot powers of 17 of the characteristic. See, we got the index 2011, and to find the coefficients from the index, we do reverse integer digits base 17, and we got 357 back. And the other representation is exponential representation. So this constructs the field with 23 to the power 4 elements in exponential representation. So in the exponential representation, the field irreducible is always chosen to be a primitive polynomial, as each non-zero element of the field is a power of the field generator. So the index of the kth power of the field generator is chosen to be k plus 1, so that the index of this field 0 is always 0. 0 is, of course, not a power of the field. All the non-zero elements are powers of the field generator, and the index of 1 is also always 1. So it's both in exponential and polynomial representation, field 0 and field 1 are represented by indices 0 and 1. Okay, now for converting the coefficients, so this is something new in version 14. So we have polynomial with integer coefficients. We want to convert it to polynomial with field coefficients. This was the field with characteristic 19. So 21 got converted to 2, 37 got converted to 18. Now we factor this polynomial, and we can convert the factors where the field elements are converted to polynomials in T. So the T is standing for the field generator. So instead of having a polynomial with field coefficients, each coefficient in the field gets converted to explicit polynomial in the field generator, where the field generator is represented by the specified variable. So we can expand it, collect it with respect to x, and then convert it to finite field, and we should get and do get the same polynomials here. Now linear algebra over finite fields. This again is something new in version 14. So first, well, we generate a random matrix of elements of finite fields. Here we use the new function from finite field index. So we can generate random integer matrix, and now this will convert all the integers to field elements with those indices. So we have random matrix of field elements. Now we compute inverse of the matrix, check that it's actually an inverse. So we got a identity matrix over the field. Now we compute matrix power. You can see that we can compute really large powers because we are in the finite field, so the elements will not keep getting larger and larger. This is a random vector of field elements, and we can solve linear equation using the matrix and the vector. Here is the solution, and we can check that indeed it is a solution of the linear equation. We got 0 equations over the finite field. So again, we have some finite field. Now we solve univariate equation, polynomial equation over the finite field. These are the two roots that this fourth degree equation has in this particular field. Or we can use field as the domain argument of reduce. So the polynomial had integer coefficients, but we specified we want the solution over the field. And here are the solutions. And here's a solve with the system of polynomial equations. We get the solutions. And here's find instance. So we have one equation, three variables, but we just want one instance solution of this equation.